Okay, so what I want to do is just to give you a very, very brief high-level overview of the tutorial and its structure. So this tutorial is about mechanism design, which is a field of game theory that has tremendous real-world impact in areas such as mechanism design, auction design, and pricing. And in this tutorial, we'll focus in particular on an exciting new approach to mechanism design called automated mechanism design that uses machine learning and optimization in order to design mechanisms based on data. So this is a very exciting topic at the intersection of machine learning, game theory, optimization, and so on. Okay, and in terms of the structure of the tutorial, just to get you up to speed, or just to remind you in case you are familiar with what mechanism design is, we'll start with mechanism design basics and a very high-level overview of what mechanism design is, and Ellen will present that part. Then we'll talk about automated mechanism design, and Tuomas will present that part. Then I'll present formal guarantees, in particular sample complexity guarantees for automated mechanism design. And then Ellen will conclude by putting this into a broader context and discussing open directions. And we'll have a 5 minutes or like 10 minutes break for questions, right, after Tuomas is speaking. But if you have pressing questions, please feel free to ask questions throughout the tutorial. Okay? And so now Ellen will start with an introduction to mechanism design.
Okay, so like Nina said, mechanism design is a field of game theory with tremendous real-world impact, and it includes areas such as pricing design and auction design. And of course, we see prices and auctions all around us. So for example, Amazon sells millions of items every day, and it has to decide how to price every single item it sells. So how should it do that? And the US government has to design spectrum reallocation auctions. So historically, radio waves or radio spectrum has been owned by radio broadcasting companies. But recently, new uses have arisen for radio spectrum, namely wireless broadband. So the US government has had to hold these massive auctions where they buy back the radio spectrum from the broadcasting companies, resell it in an allocation that will hopefully be more efficient. So these radio spectrum auctions are a huge computational challenge and also have a lot of interesting theoretical questions. Sourcing is the process by which corporations acquire goods and services for their operations. And sourcing auctions are really challenging because of complex interactions between preferences, prices, and constraints. And Tuomas, who will speak next, has had a company in the past that held these spectrum allocation auctions, and he was moving around billions of dollars. And finally, large internet companies, of course, get huge amounts of their revenue from ad auctions. So when you make a Google search, you're going to see these sponsored search suggestions on your page. And the way this works is that when you make this search, an instantaneous auction goes on where advertisers bid on the opportunity to show you an ad. And as you can see, huge fraction of these companies' revenue come from these ad auctions. So this tutorial is about automated mechanism design, which is a new approach to mechanism design which uses optimization and machine learning to design mechanisms based on data. And automated mechanism design helps overcome the challenges that have been faced by economists, namely the challenges of traditional and manual mechanism design have faced these major roadblocks because we don't even know how to sell 2 items to 2 bidders optimally or in a revenue maximizing way. So in this tutorial, we're going to cover real-world success stories, and we're also going to cover some statistical guarantees, which we believe are using tools that should be of independent interest to machine learning theory more generally. Okay, so now I'm going to start off with some mechanism design basics just to make sure everybody is on the same page and everybody's up to speed. So at a high level, a mechanism for a sales setting, there's going to be a set of items for sale and a set of buyers who want to buy those items. And at a high level, what a mechanism determines is who should receive which items and what they should pay. So for example, maybe there's a coffee and a muffin for sale, and so there are two buyers. This buyer values the coffee for $2, the muffin for $3, and the pear for $6. And we want to figure out what prices should we set, who should get the items, and what should they pay. So I'm going to go through a couple examples of some classic mechanisms, starting off with posted price mechanisms. And these are going to sound very familiar because we interact with them every day. So in this mechanism, the mechanism designer sets a price per item. So maybe we set the price of the coffee to be $1.50, the price of the muffin to be $3.50. And the buyers are going to buy the bundle of items that maximize their utility. And utility is defined to be their value for the items minus the price of the items. So for example, this buyer is going to have a utility of 50 cents for the coffee because that's their value minus the price. They're going to have a utility of negative 50 cents for the muffin, and they're going to have a utility for the bundle of the pear at $1 because that's the value minus the price. So they're going to buy the bundle, the coffee and the muffin. That maximizes their utility. Another classic auction is the first price auction. So this, in this auction, the bidders submit bids for some item, some single item. And so maybe the buyer's bids are $9, $7, $6, and $5. And in this auction, the highest bidder is going to win, and they're going to pay their own bid. So it's a first price auction. A similar auction is the second price auction, where this time the highest bidder again wins, but he pays the second highest bid. So in this case, this blue bidder is going to pay $7 because that's the second highest bid. And this auction has many nice qualities that we're going to talk about later on. We can hope to maybe get more revenue from the second price auction by adding a reserve price. So here the auctioneer sets some reserve price R, which is just a real value, and the highest bidder is going to win if their bid is greater than or equal to the reserve price. And they're going to pay this maximum of the second highest bid and the reserve. So for example, if we set the reserve price to be $8, we can get more revenue than we did in just the plain second price auction, because again, the highest bidder is going to win because their value is greater than the reserve, and they're going to pay the maximum of the second highest bid and the reserve, which is $8. So the revenue is going to be $8. But if we set the reserve price too low, then we kind of revert back to the second price auction. So if we set the reserve to be $6, then we get a revenue of $7 because that's the maximum of the second highest price in the reserve. And just as a bit of history, the second price auction was introduced to the economics community by William Vickrey, and it's sometimes referred to as the Vickrey auction. And Vickrey won the Nobel Prize in economics. And one of the reasons we really care about second price auctions is because it maximizes social welfare. It's a mechanism that maximizes social welfare, which is the value of the bidders for the items that they receive. And buyers are incentivized to bid truthfully. And we're going to talk a lot more about incentives in a couple of slides. And since then, many computer scientists have also studied the second price auction in the computer science economics literature. This is just a tiny subset of those papers. Okay, so now that we've seen a few different examples of mechanisms, I want to go over some notation so we can talk about mechanisms slightly more formally. So throughout this talk, there are going to be M items for sale and N buyers. Each buyer, I, is going to have a value, VI of B, for each bundle B. So B is a subset of the M items. And we're going to denote all of buyer I's values for all 2 to the M bundles as this vector. Okay, so for example, maybe there are 2 items for sale. We always assume that all the buyers value the empty set for $0. And maybe he values the coffee for 2, muffin for 3, bundle for 6. So our vector representing all of his valuations is going to be this length 4 vector. So here I've just superimposed his values for these items onto this vector. Okay, so now what exactly is a mechanism for these sales settings using this notation? So a mechanism, which we'll denote as M, is defined by an allocation function and a payment function. And again, an allocation function determines which buyers receive which items, and a payment function determines what they pay. Revenue is the sum of the buyer's payments, and we're going to denote this throughout this talk as revenue sub M of V1 up through Vn. So given their values, what is the revenue of this mechanism? And like I mentioned, sometimes buyers are not incentivized to bid truthfully. So sometimes a mechanism might require buyers to submit bids, which I'll denote as VI tilde. And if the buyers are being strategic, then their bids might not equal their true values. But this brings me to some properties we would like our mechanisms to satisfy. The first of which is incentive compatibility. We would like our mechanisms to be incentive compatible, which means that all buyers are incentivized to bid truthfully. And we would also like our mechanisms to be individually rational, which means the agents have nothing to lose by participating in the mechanism. So no one's going to walk away with negative utility. So now I'm going to describe incentive compatibility a little more. So I'm going to show you why the second price auction is incentive compatible. And remember, this is where the highest bidder wins and pays the second highest bid. So the claim is that every bidder is going to maximize their utility by bidding truthfully. And remember, utility is their value for the good minus their payment times 1 if they actually win. So let's assume that all the other bidders are bidding truthfully. Why would I not want to bid above my own value for this good? Well, let's say that I'm the winner, so when everyone's bidding truthfully, I'm the winner, right? So my true value is above everyone else's values. Why wouldn't I want to bid above my value? Well, I'm still going to be the winner, and since I pay the second highest bid, my payment is not going to change, so I have no incentive here to bid above my true value. And what if I'm the loser, so my value falls below some other bidder's value? Why wouldn't I want to raise my bid in this case? Well, I might become the winner if I raise my bid to the highest bid, but I've raised my bid so far that I'm going to be paying something that's higher than my true value. So I'm going to walk away with negative utility. So I don't want to raise my bid in this scenario either. Okay, so we've seen why I wouldn't want to bid above my own value. So why wouldn't I want to bid below my value either? Well, if I'm the winner, right, I might become the loser, but that means that I shifted from a non-negative utility to 0 utility. So I have no incentive to do this. And finally, if I'm the loser and I shift my bid even lower, then I'm still going to lose. So I have no incentive to bid untruthfully in this scenario either. So we've seen I don't want to bid above my value, I don't want to bid below my value, so I might as well bid my own value. So that's incentive compatibility. Individual rationality, I am no worse off by participating in the mechanism. I'm not going to walk away with negative utility. And the second price auction is individually rational because assuming that everybody bids truthfully, like we saw we can assume, the bidders are either going to pay nothing if they lose, or they're going to pay something that's at least as low as their own value. So they're going to walk away with at least non-negative utility. So the second price auction is also individually rational. Okay. So now I want to talk about individual rationality and incentive compatibility. Since they're such fundamental concepts in mechanism design, I want to talk about them slightly more formally. And to do this, I'm going to introduce a standard assumption that's been made for decades in economics and is actually very natural from a machine learning perspective as well. And it says that buyers' values are defined by a probability distribution over all the possible values they might have for all the bundles of goods. So for example, what we're assuming is that there's some distribution D from which the buyer's values are drawn. And again, these are valuation vectors. That's how we're representing them. So there's a distribution over these valuation vectors. Okay. And introducing this assumption allows me to now define 3 different variants on incentive compatibility. So we've got ex ante, ex interim, and ex post incentive compatibility. So let's think about the very beginning of the whole mechanism. So at the very beginning, we can assume that all buyers know the valuation distribution. We can assume that for now. But no values have yet been drawn from this distribution. And mechanism is ex ante incentive compatible if, in expectation over all bidders' values, you're incentivized to bid truthfully. Okay, and now we can move to the next step in the mechanism where we've drawn the bidders' values from this distribution, and every bidder knows their own value, but they don't know anyone else's value yet. So we're at this middle dot. And ex interim incentive compatibility says that in expectation over all the other bidders' values, I'm incentivized to bid truthfully, no matter what my value is. Okay? And finally, we can move to the next step in the mechanism where I know my own value and I know all the other bidders' values. And ex post incentive compatibility says that for every bidder, given all the other bidders' valuations and my own valuations, I'm still incentivized to bid truthfully. And as you can probably imagine, we can similarly define ex ante, ex interim, and ex post individual rationality, but I won't do that right now. And on another historical note, Hurwitz introduced this notion of incentive compatibility. He won the Nobel Prize in economics. And there's kind of a fundamental concept in economics that, kind of waving our hands a little bit, allows us to assume incentive compatibility without loss of generality. And this basically says that if for some mechanism, you start off with some mechanism, and all agents are incentivized to follow some strategy, some fixed strategy, maybe it's not a truthful strategy, but it's some strategy, we can create a new mechanism with the same prices and allocation where agents are incentivized to bid truthfully. And it's pretty simple. We just take their values, their true values, we run it through whatever strategies they use, and then we input those strategic bids into the original mechanism, and we get whatever outcome that mechanism produces. And so, of course, in this mechanism, the buyers are incentivized to bid truthfully. And so kind of colloquially, we could say that the mechanism lies for the agents, so the agents don't have to lie. Yep. Yeah, we assume they know about the mechanism, yeah. Okay. So now I want to move into revenue maximization. We've seen kind of the fundamentals of mechanism design, and now I'm going to tell you about kind of one of the most beautiful results in mechanism design, which is the optimal single item sales mechanism. So this was discovered by Meyers in 1981. It's the optimal single item sales mechanism, single item multi-bidder. And economists typically refer to revenue maximizing mechanisms as optimal mechanisms. So that's the terminology we're using here. And he also won the Nobel Prize. And so some kind of like intuition behind Meyerson's optimal auction. So what is the problem with the second price auction? Why wouldn't the second price auction be revenue maximizing? Well, let's think about a scenario where we've got one strong bidder and one weak bidder. And generally, the strong bidder's bids are much larger than the weak bidder's bids. Typically, the strong bidder is going to be winning, and he's going to be paying the weak bidder's bid. Because it's the second price auction, highest bidder wins, pays the second highest bid. So this is kind of unfortunate. It's going to leave a lot of revenue on the table, because if the strong bidder's bids are much larger than the weak bidder's bids, he'd be willing to pay a lot more. So what Meyerson's auction does is it kind of boosts these weak bidders' bids to create competition for the strong bidder. So it kind of artificially boosts his bids. And kind of the amazing thing is that Meyerson's optimal auction maintains incentive compatibility nonetheless. So I'm going to tell you what Meyerson's optimal auction looks like now. So Meyerson's optimal auction works in the case where the buyer's values are independently distributed. Not identically, but independently distributed. So we assume that buyer i's value has a distribution with a probability density function Fi, a CDF capital Fi, and support in 0, 1. And we define a virtual value function as follows. Phi I of t is defined to be this value. So this is a function, we call it the virtual value function. So what we do is we solicit bids from these buyers. We map their bids through this virtual valuation function, so we get these virtual values. And if all of these virtual values are smaller than 0, then we don't allocate the item. But if some buyer has a non-negative virtual value, then we allocate the item to the buyer with the highest virtual value. And in words, we charge the winning bidder their threshold bid, which is just the smallest they would have to keep bidding in order to keep winning. And you can see that in math written here, if you're curious. Meyerson's optimal auction was later extended to selling multiple units of a single good. And a kind of interesting fact connecting this back to the second price auction is that when the buyer's values are not only independent but identically distributed, Meyerson's optimal auction is equivalent to a second price auction with a carefully chosen reserve. So that's what we know about first price, or what we know about single item auctions. But when we try to sell multiple items, there are huge roadblocks. We don't even know how to sell 2 items optimally in a revenue maximizing way. There's been tons of work in this field from both the economics community, the computer science community. And next, Tuomas is going to tell you more about automated mechanism design for multi-item auctions.
Thanks, Ellen. So as Ellen said, it's kind of amazing that we don't even know how to sell an apple and an orange so as to maximize revenue. And obviously, real-world selling situations get much more complicated because there aren't just an apple and orange, there can be many different things. All right, so that's one of the main motivating scenarios for automated mechanism design. So automated mechanism design is something that my then student Vince Kornitzer and I started doing in 2001. And the idea was that we solve the mechanism design not as a paper and pen exercise, but we actually formulate it as an optimization problem that is solved algorithmically with search algorithms, optimization algorithms, and so on. We built a system for doing that, and the idea is that we create a mechanism for the specific setting at hand rather than a class of settings. And that's possible through the automation because, as humans, we always really have to look at the class of settings. We can't possibly have the time to analyze every possible situation in the world and make a custom mechanism for the setting. And I'll give you some examples of this in a moment. But what are the benefits of this? Well, one is that it can lead to greater value of the designer's objective than known mechanisms. One of the main examples throughout this tutorial is greater revenue. When we want to sell things, we often want to maximize revenue, and I'll show you that we can get much higher revenue with these mechanisms. But that's not the only kind of objective you might want to look at. You might want to look at fairness objectives and bundles of different objectives and so on. And when you actually design to the specific class at hand, you might actually be able to do better than you could do for a whole broad class of settings. Secondly, and related to the first point, sometimes this circumvents economic impossibility results. And it always minimizes the pain caused by them. And what do I mean here? Well, there are seminal impossibility results in mechanism design coming from economics that say that in a certain class of situations, nothing works. And let me give you one example, maybe the most famous example. So the Meyers and Satterthwaite Theorem for trading from 1983 says that even if there's just one item for sale, one seller, one buyer, we cannot come up with a mechanism so that the good will trade hands whenever the buyer values the good more than the seller, as long as we require budget balance and it's voluntary to participate in the mechanism. So that seems like a very bad impossibility result. Yet we see trade all the time, and not just one item trade. So turns out that the Meyers and Satterthwaite theorem sometimes doesn't bind at all. For certain valuation distributions of the buyer and seller, there is no impossibility. And for other valuation distributions, the inefficiency that stems from the impossibility result is rather small. And when you optimize to the distributions at hand using automated mechanism design, you get the minimal pain, the minimal loss in efficiency. Then this can also be used in new settings and for unusual objectives, settings that nobody has had the time to actually solve before, or objectives that people haven't had time to solve. It can yield stronger incentive compatibility and participation properties. So if you think about what Ellen says, she's talked about ex ante, ex interim, and ex post. So sometimes we can actually get further to the right side in that figure while not giving up anything by using automated mechanism design that's specific to the distribution. And then it shifts the burden of design from human to machine, which is, I guess, always a good thing. So one of the motivating examples for me why I started thinking about this was our work on sourcing auctions. So we were doing strategic sourcing where governments and companies buy goods and services from their suppliers, often for, let's say, a year ahead, oftentimes hundreds of millions or billions of dollars per auction. And back in the kind of early 90s, with companies like free markets and Ariba and so on, the most common auction mechanism for sourcing was a descending price auction for pre-bundled lot. And that is completely prior-free. It doesn't have any information about the priors. And in sourcing, oftentimes a buyer has a lot of prior information about the supply base. So it just seems silly that as a first step of your sourcing process, you would throw away all the information that you actually have. All right, so some of you may actually wonder about the wording automated mechanism design versus algorithmic mechanism design. These sound similar, but they're completely different things. In automated mechanism design, we are designing the mechanism automatically. In algorithmic mechanism design, it takes a viewpoint that you can't solve the NP-complete winner determination problem, and therefore we are manually trying to design mechanisms that run in worst-case polynomial time. So again, while they sound similar, they're totally different. All right, so here's a picture of classical versus automated mechanism design. So in the classical approach, you prove general theorems, possibility results and impossibility results. So for example, you might say, okay, for this class of setting, this mechanism accomplishes properties X. And for that setting, no mechanism accomplishes properties Y. And then you publish the results, and then people draw intuitions from the results, and when they face a real-world problem, they apply the intuitions manually to build a mechanism that's somehow loosely motivated by the theory, and then they apply the mechanism to the setting at hand. In automated mechanism design, we're actually taking the mechanism design framework quite literally, and we're building the software once, we're taking the real-world mechanism design problem that appears, feed it through the software, and apply the mechanism directly. All right. So in the first generation of automated mechanism design, the input representation was what we call flat. So you would actually discretize a type space if it wasn't already discretized, and I'll talk about what that is. And you would have kind of a table-based representation of the input and the mechanism. So now I'm going to run by you what that was, but realize that we're going to get into some smarter things later, so don't walk away from the tutorial just by seeing this. So an instance of the automated mechanism design problem is given by a set of possible outcomes. These are the choices that we can choose among. And the outcomes can include allocations and payments. Then there's a set of agents, and for each agent, we have a set of possible types. The types characterize the agent's preferences. Then there's a probability distribution over these types. In general, this can be a joint distribution also, but the hardness results that I'm going to present in 2 slides actually apply even if you have a separate probability distribution for each agent. And then there's a utility function that converts the outcome and the type to a utility, a real valued utility. So if you like to think about it the other way around, you might think that, okay, we don't know the agent's utilities, then the type is really like an index to the utility function. It talks about which utility function the agent might have. And then we have a distribution over those types. So we know some distribution over the agent's preferences, but we don't know exactly the agent's preferences. Then there's an objective function. What are we trying to accomplish with our mechanism? This gives a value for each outcome for each combination of the agent's types. For example, it might be payment maximization. We want to maximize expected revenue. But it can be other things also, like maximizing welfare, trying to allocate the goods so that the buyers in aggregate have maximum value from the goods, or some combination of thereof. Or it could be fairness, etc., etc. Then there's restrictions on the mechanism. First of all, are side payments allowed? In some situations, side payments aren't allowed, for example, in voting. In other settings, like selling settings, money is allowed. Is randomization over outcomes allowed? It turns out that the optimal single item auction, by which when we say optimal auction, we mean revenue maximizing. In the single item setting, there's no power to randomization. The optimal auction is deterministic. But already when you have 2 items, the optimal auction is actually randomized in general. But we still might want to have deterministic mechanisms because they're easier to understand and there's kind of less variance and so forth. And actually there are very few, if any, real-world mechanisms that are fielded that are randomized. Then what concept of manipulability is used? What incentive compatibility notion? Are we talking about ex ante, ex interim, or ex post? And what participation constraint is used? Participation just means that we are motivating the agents to participate. And what could those constraints be? Well, one is none. We don't have to motivate them because somehow they have to participate. Well, let's say in a voting situation. Well, if you're in you're a citizen, you know, the president is going to be your president no matter what you voted. So it's not a choice as to whether you're in or out. Or it might be ex interim or ex post. Oftentimes in auctions and exchanges, you have to motivate people to participate because they have the option of not participating. All right, what's the output then? The output is a mechanism. And again, here we were in a table-based world. A mechanism maps combinations of agents reveal types to outcomes. So combination means one type per agent. So whatever their reported types ended up being, that maps to an outcome. And a randomized mechanism maps, of course, to a probability distribution over outcomes. And also, the mechanism specifies the payments in cases where payments are allowed. What are the properties of the mechanism? Well, it's non-manipulable according to the given incentive compatibility constraint type. It satisfies the given participation constraint type, and it maximizes the expectation of the objective function. Okay, so this of course sounds great. Hey, now we don't have to do anything by hand, but computational complexity is a big problem here. And before we get to that, let me actually give you a motivating example why this might be a good idea. So there's this famous impossibility result called the Satterthwaite Theorem, Satterthwaite Theorem actually, that says that if you are in a voting setting and you have at least 3 candidates, the only dominance-strategy incentive compatible mechanisms are dictatorial. Now, that sounds like a sweeping impossibility, but there are actually islands of possibility in that space. So let me give you an example. So now, these x's on that slide, these are type vectors. In each type vector, there's one type for each agent, all right? So there's an island within that space called quasi-linear preferences, where there are actually mechanisms that do work. So if we have our probability distribution sitting completely on that island, we are circumventing the impossibility result completely. And by the way, this wasn't discovered by automated mechanism design. This was known much before that. So we have possibility in that island. Then, if we think about the impossibility result, there might be some sort of a red distribution where the impossibility result really does bite, and we have impossibility. There might be this blue distribution, which is outside the known manual possibility island, but it still has possibility. And there might be this blue island here, which is a totally new island, where you have possibility. It was just not known. All right, so let's talk about complexity. The following 4 objectives, any one of them is NP complete to design the mechanism for, even if there's just one buyer, just one agent, and even if we want to just design a deterministic mechanism, or in particular because we want to design a deterministic mechanism. The first one is maximizing social welfare, which is the sum of the agent's values over the allocations in a world where no payments are possible. Turns out that in a world where payments are possible, there's a mechanism that does this, and that's known, and I'll talk about that in a second. Second, maximizing the designer's utility over outcomes in a world where there are no payments. Or maximizing a general objective, even just a linear one, that doesn't regard payments, even when payments are possible. And fourth, expected revenue. And for the purposes of this tutorial, that's the one where we are mostly interested in. We are trying to design revenue maximizing multi-item mechanisms. So that's NP complete if you want to design a deterministic mechanism. And what that actually starts to tell us, that maybe it's not a coincidence that the literature of manual mechanism design has gotten completely stuck in multi-item revenue maximization. Nobody knows even how to sell 2 items. This is saying that, well, the problem is NP complete. So maybe there's a reason. Maybe there can't be a concise characterization of the mechanism unless P is equal to NP, or unless the characterization itself can make reference to solving NP complete problems, like now solve that, now solve that, now solve that, and so forth. But it can't be kind of an analytical characterization like the Meyers auction. Now, these are in polynomial time if you allow designing of randomized mechanisms and you have a constant number of agents. Then it's just a constant size LP, and you can solve that with linear programming. All right, so that was for the table-based representation, and it has also a problem with the input. And no matter what you really actually use as your representation, you're going to have this input problem. So it's not just that the computational complexity is hard in the mechanism design box. It's also that the input is huge. So there's going to be an exponential allocation space. Any one of the items can go to any one of the agents or to none of them. So the number of allocations is agents plus 1 to the power of items. And even if you have these product distributions where you don't have any correlation between the different agents' type spaces, even for one agent, the support of the type distribution can be doubly exponential. So let's say for simplicity that each bundle for a given agent can take any one of k values, just to keep it simple, so it's discretized. You have 2 to the power of items bundles, so the support of the probability distribution is doubly exponential, k to the 2 to the items. So this means that you can't even represent the input to these design problems except in tiny problems, maybe 2 or 3 items. Okay. So how do we get around these computational difficulties and input largeness difficulties? And notice it's not just a computational question of, hey, I can't take the input. This input can't be sitting around anywhere because nobody can have enough representation space to store it and not enough experience to gather it, etc. All right, so Anton Likodedov, who's my student back then, and we came up with 2 ideas to try to cut down on this complexity. And one side is kind of trying to get scalability, and the other side is trying to avoid the need to discretize the type space. So oftentimes we don't really have a discrete type space, we have a continuous type space. The first idea was not to assume that the valuation distribution is given, like we usually assume in auction design or sales system design in economics. Rather, let's only assume we have samples from the distribution. Okay? So now, my complexity is not out of hand. I can have a list of samples, I can store it. Now, of course, the list of samples isn't as good as the whole distribution, but at least I have something that's potentially practical. And second, instead of trying to design the mechanism from scratch in a table-based representation, maybe let's take some sort of parametric class of mechanisms where each mechanism in the class has good properties, let's say incentive compatibility properties and individual rationality properties, and then let's optimize the parameters so as to try to maximize our objective over that class. All right? And now I can have more complex classes with lots of parameters or simpler classes with fewer parameters. So I can control my computational complexity, and as we also will talk about, we can control the sample complexity of these things. All right. So there's an unknown distribution over valuations, and we use a set of samples to learn a mechanism that has high expected revenue. And there's been work on the multi-item case now on that, as well as on the single-item case. So more formally, if you think about it as a learning problem, our goal is the following. Given a large family of mechanisms and a set of buyers' values sampled from an unknown distribution D, find a mechanism with high expected revenue on the real distribution D, which we don't know. And the approach that we'll take is that we'll try to optimize a mechanism to the samples that we do have. And now there's 2 questions. How do we optimize? So we get near optimal on the samples. And then if we do that, how close are we to optimal on the real distribution, which we didn't know? So I'll talk about the optimization problem now, and later in the tutorial we'll cover the sample complexity side. But first, what do we mean by sample? And there's some flexibility here. We could define a sample in many different ways, but for the purposes of this tutorial, we define the sample as being a full draw of valuations for every agent. So every agent has a value for every bundle. We see basically this type of table in every sample. So it says for every agent, what's the value of their, that they have for every bundle. And then we can have n of these samples. Okay, so that was the don't assume valuation distribution, only assume samples. Now the other side is on the optimization side. Instead of trying to optimize from scratch in this table-based representation, let's do automated mechanism design as a search in a parametric mechanism class. And I'm going to start from the first things we did, and then we'll talk about some more advanced things later, like how do we decide what kind of mechanism class we can afford to use given a finite set of samples. But the mechanism class that I'm going to talk about is probably the most famous auction class in the auction literature. We're going to start from that, and then we're going to transform it to something better, higher revenue. This is called the Vickrey-Clark-Groves mechanism, or VCG. Ellen mentioned the Vickrey auction. This is the multi-item generalization of the Vickrey auction. It's a fundamental building block for multi-item, multi-bidder automated mechanism design of deterministic mechanisms, as you'll see. So now, when we're optimizing in this class, we are optimizing over deterministic mechanisms because they're practical, because we know how to do it, and so forth. So some of the theory that we'll show later in this tutorial, actually all of the theory, applies to randomized mechanisms as well, but I'm going to just, for now, talk about the deterministic mechanisms. So this is the VCG mechanism, which was designed manually, is a multi-item, multi-bidder incentive-compatible auction that maximizes social welfare. It's incentive-compatible in the ex-post sense, in that even in hindsight, if I knew exactly what the other bidders bid, I'm still better off telling the truth. And it's also ex-post individually rational, in that even in hindsight, I can't regret having participated. In particular, if I win nothing, I pay nothing. And what's social welfare? That's a sum of the buyer's values for the items they are allocated. So here, we are just taking the view that we are this altruist and we just want to allocate these goods so as to maximize goodness in the world, not including ourselves, by the way. So the seller is not included. This is just the bidders. We want to allocate the goods to the bidders who value them the most, so to make best use of the goods. All right. How it works, first, each bidder submits a bid for each bundle of items. And there's been actually quite a bit of work on how do you make this step simpler with more sophisticated structured bidding languages and preference elicitation techniques and so on, but we are not going to talk about that in this tutorial. So don't worry about that complexity now, just say that everybody bids on every bundle. All right. So now the notation is that there's an allocation of M goods where BI is the bundle of goods that bidder I gets. So this means that the bundles are all subsets of the set of goods, maybe empty subsets, and the subsets don't intersect. The social welfare is the sum of the bidder's values, where each bidder's value is the value the bidder gets for the bundle that they got, so VIBI. And we'll call that SW for short, for social welfare. Then B star, we'll call B star the optimal welfare. So this is the B star is the allocation that maximizes social welfare. So now if you look on the right, here's an example. We have two bidders, 1 and 2. We have two items, coffee and a muffin, and we have the values shown in black. So bidder 1's value for item 1 is $1 and so forth. Now, the optimal allocation, if you eyeball that for a second, is to allocate both goods to bidder 1, because you get 2.5, and nothing to bidder 2. And you can convince yourself that there's no way to get higher social welfare than 2.5. All right? SW minus I is a social welfare of an allocation not including bidder I. So how well off are the other bidders in the allocation? And B minus I is a notation for social welfare maximizing allocation if bidder I hadn't participated. So if bidder I hadn't submitted any bids, had stayed at home, the other guys would have won more things, and what would that allocation have been? And in the VCG mechanism, you choose the optimal allocation overall, but the bidder doesn't pay the bidder's own valuation for the goods that she got. Rather, the bidder pays the social welfare of the others had she stayed at home, minus the social welfare of the others. So this is really the negative externality that bidder I imposes on the others by showing up. So bidder I showed up, took some items home, therefore those items didn't go to the other agents, therefore there was a negative externality. How big was that negative externality? Well, that's how much bidder I has to pay. All right? So let's run that through this example. The best allocation, if bidder 1 had stayed at home, would have been to give both goods to bidder 2. So the social welfare of the others would have been 1, while in reality the social welfare of the others was 0. So bidder 1 has to pay 1 minus 0, which is 1. Okay? Now, you might see the problem here. Bidder 1 values her allocation at $2.50, but only paid $1. So this is not, somehow this smells bad. It smells that we're not maximizing revenue. I'm not saying that you would ever be able to extract the whole surplus, the sum of the bidder's values. But this just seems low, right? So what can you do? Well, what if you made an additive boost to the social welfare of the allocation that would happen if bidder 1 had stayed home? And let's call that, that in the red 1.49. So we got to give an additive boost to the social welfare of the others if bidder 1 had stayed at home. So now bidder 1 pays 1 plus 1.49 minus 0, which is 2.49, almost a full 2.5. Okay. So we're now somehow tweaking the VCG mechanism to make bidder 1 pay more. All right. So now I'm going to tell you what the general pattern of tweaking is, but first I'm going to give you the general VCG mechanism as it was originally introduced. So first we compute the social welfare maximizing allocation, which is the argmax of allocations of the sum of the bidder's values. Then we're going to compute for each bidder the social welfare maximizing allocation without that bidder's participation. Then we are going to compute how much that bidder has to pay. And that's just how much happier everyone would have been if that bidder hadn't participated. All right, so we talked about this already. This is just putting it in a kind of a nice form where I can add some things now. So the idea of the boosting is that we can boost every allocation with some positive, with some constant lambda. They could be positive or negative. So I'm going to add to the social welfare function that we're maximizing in step 1, the lambdas, and then I'm going to add the lambdas also in step 2, and I'm also going to add the lambdas in step 3. Nothing else going on except that I'm giving this additive boost to allocations, and it can be 0. Of course, now you might guess that there's an issue of optimizing those lambdas. What should they be? And that's indeed going to be an issue we're going to talk about. But we can do another thing also, which we can take positive weights W, and we can weight the bidders. So we can multiply the bidders' values with W's, as you can see here, in steps 1, 2, and 3. And now we're going to get a class which we call, or which are called affine maximizer auctions. This is a class that was introduced by Roberts in 1979. And this class is still incentive compatible, ex post. So we are free to make any of these changes, and we're not going to violate incentive compatibility. and also individual rationality is maintained. So this gives us a class, if you think about the pattern that I suggested, it gives us a class where we have the good IC and IR properties, and now we can just tweak the parameters so as to increase revenue. So this is one of the parametric classes we optimize over. Now, what Robert showed is that in a setting of an allocational auction, where the bidders don't just care about what they get, but also potentially what the other bidders get. So they might like that their friends would get more goods than their enemies and so forth. This is the only incentive compatible mechanism. Only one. Not the only revenue maximizing one, only one. Okay? Now, and so in a combinatorial auction setting, it's not quite the only one. There are other things. But Lavi Muolem and Nissan have a paper that show it in a certain sense under an additional non-bossiness assumption and a scale-free assumption. These are the only mechanisms even for combinatorial auctions. So that's an additional motivation why we look at this. All right. Virtual valuation combinatorial auctions is a class that we introduced with Anton Likodedov. It's like the affine maximizer auctions, except with a restricted boosting space. So each lambda is replaced by the sum of the bidders of a bidder-specific lambda of the bundle at hand. So now we have a somewhat restricted lambda space to optimize over. And again, steps 1, 2, and 3 are the same. All right, so now let's talk about computational considerations here. Downsides, expected revenue is not convex in the parameters. And there's no polynomial time algorithm capable of determining for a given set of valuations whether one parameter vector is better than another, unless p is equal to np. On the positive side, for any given valuation vector, the revenue has only one maximum in any parameter, and the expected revenue is continuous and almost everywhere differentiable. So that gives us kind of two algorithm families we could think about. One is grid search, and the other is kind of some sort of hill climbing. For example, starting from VCG and then hill climbing in the parameter space. In either method, we evaluate how well we are doing by taking samples from the distribution and evaluating the revenue at that parameter vector. Okay, so the first algorithm is AMA star. It's iterated grid search in the AMA parameter space, the affine maximizer auction parameter space, with the grid tightened and recentered around the best grid point in the previous iteration. VVCA is the similar kind of search, but now in the VVCA parameter space. Of course, the grid search is not scalable to large problems due to the cursor dimensionality. And what we saw is overfitting already on the third iteration. So we were actually getting better and better on the samples, but we were getting worse on the real distribution. So that is actually one of the motivating practical things we saw that motivates the learning theory that we'll talk about later. And then the basic local AMA search starts at the VCG and then runs gradient ascent in AMA parameter space. We were running Fletcher-Reeves conjugate gradient ascent, but there's nothing magical about that choice. All right. Now, one more thing here on the optimization side is that can we somehow reduce the complexity by selecting the gradient ascent direction using economic insights? And the high level idea here is that if bidder I pays in an allocation much less than her value in the allocation, she should pay more. And that gives us kind of families of algorithms for doing smarter gradient ascent. And here's one of the algorithms for optimizing the affine maximizer auction parameters. First, we sample the valuations from the prior distribution. Then we start at the VCG. So all the weights are ones, all the boosts are zeros. Then for every sample point that we draw from the prior, we compute the revenue loss of the winning allocation. The revenue loss from a bidder is the difference between the bidder's valuation and her payment. And the revenue loss is the sum of the bidder's revenue losses. And the revenue loss of an allocation, then, is the sum of the revenue losses of the samples associated with the allocation. We make a list of these allocations in decreasing order of revenue loss, choose the first allocation from the list, If the list is empty, we're done. We're at the local optimum. Otherwise, we run gradient ascent now in the mu, or that's the weight, W that we had before, and lambda A subspace of the AMA parameter space. So now we got 2 parameters to optimize over, which we can run quickly. And if the value didn't change for either parameter, then we're at the local optimum with respect to that, and we move to the next allocation to step 5. Otherwise, we move back to step 3. All right. Then there's a similar kind of idea for the VVCA, auction optimization, and here are some results. So first, let's talk about 2 items, 2 bidders. Sounds simple, but even that was unknown. So here we have value of a bidder for item 1 and item 2 drawn from a prior distribution with the density function Fi. So the different bidders can have different priors. And the value for the bundle is the sum of the values of the items plus some constant C, where C is drawn from a distribution Fc. We have 3 settings on the slide here. The first setting is the simplest one where there's no complementarity, so C is 0. And we're drawing the valuations for the items for both agents uniformly from 0, 1. The VCG gives revenue 2/3, and then the other auctions give a revenue lift ranging from 17% to 32% over VCG. In setting 2, we have some complementarity, but we still have symmetric distributions. And again, you can see that there's a significant revenue lift over VCG. And in setting 3, we have asymmetric distributions and complementarity and substitutability. And there you can see that the local search methods don't do as well as the grid search methods, so they do sometimes in practice get stuck also in local optima. Now, it was actually quite interesting later on with the same technology, when we looked at setting 1 in more detail, we started to see what are the things that actually allow you to get more revenue. And generalizing the mechanism design from what's called mixed bundling auctions with the reserve prices, where you either sell all of the goods separately or as one big bundle, but you have reserve prices, to VVCAs, created no extra revenue. But then moving from VVCAs to AMAs did give extra revenue. So this type of computational methodology allows you to also get kind of qualitative understanding of where the revenue lift comes from. All right, scalability experiments. This is 3 items, number of bidders on the x-axis, and you can see that it's sub-exponential, and the local search methods are much faster than grid search, of course, which is not even shown here, but the economically motivated local search methods are better than the naive gradient ascent, which is the red line. Here's scalability experiments for a fixed number of bidders, varying the number of items. So that's about exponential there. Again, the economically motivated ones are better than the straightforward gradient ascent. And then anytime performance. So you also don't have to run these to convergence. You can, even large problems like 7 items, 7 bidders. Well, you might say that this is not large in the Amazon scale, but it's large compared to what was possible before. You can see that you get most of the benefit up front, so you really don't have to run these to completion. Now, a couple of more ideas. One is incremental automated mechanism design. Here, the idea is that we are not going to design somehow from scratch, and we're not going to design within a parametric family. We're going to start from a naive mechanism, which is highly manipulable, and then we're going to start to find those manipulations, and we're going to fix them. If you think about automated mechanism classes, this would be a 3rd kind of approach. So we start with some manipulable mechanism M. We find some set of manipulations F. Here a manipulation is given by an agent I, a type vector of all of the players, and a better type report. In other words, a beneficial lie for agent I. And of course, there's a lot of choice here. Do we find one manipulation, one per player, the best manipulation, best per player, or all of the manipulations, and so on? 3, if possible, change the mechanism to prevent many of these manipulations from being beneficial. And how do you change the mechanism? Well, the outcome that the agent who had a beneficial lie got has to become worse, or the outcome they would have gotten if they told the truth has to get better. But still there's a lot of choice as to which ones do you fix and in what order and so forth. And furthermore, the problem is that as you fix some of these manipulations, some other manipulations might become beneficial. And 4, repeat from step 2 until termination. And there are many instantiations. In the paper we had a couple. One of them reinvented the VCG starting from just the first price auction. And another reinvented plurality with runoff voting from just starting with plurality. All right. And now the newest in incremental automated mechanism design nowadays is surprisingly, or maybe not surprisingly, deep learning. And this is work by David Parks and his colleagues. The idea here is that we are going to get feedback from samples, revenue, and each bidder's regret. In a given mechanism, how much did the bidder regret having done what they did compared to having done what would have been the best in hindsight? They have a fully connected multi-layer feed-forward neural networks that learns near-optimal, near-incentive compatible auctions. And here's one example from the paper. There are other structures as well. So here we have the additive case where there's no complementarity or substitutability in the preferences. We have the bids for each player for each item here as input, and then as output we have the allocation probabilities of the items to those bidders. We also have a payment network here that takes the same input but has the payments of the different players as output. And how they learn in this, they actually put into the learning objective the revenue, but also penalizing the regret and penalizing non-individual rationality. And then they use generalized Lagrangian optimization to optimize the network so that it becomes almost incentive compatible, almost individually rational, and high revenue. And they have several results in the paper, but here is one where they reinvented an optimal mechanism by Manelli and Vincent from JET 06. Now, automated mechanism design isn't just for sales mechanisms, it's also been used for combinatorial public goods. We did it a little bit also in real-world industrial sourcing, although most of our sourcing auctions we didn't use it for. Divorce settlement mechanisms, turns out that sometimes you have to burn some of the goods, and that's actually part of the optimal mechanism. Facility location problems, and that's also for product portfolio generation. Reputation and recommender systems, Jurka and Faltings have done a lot of work on that. School choice and other mechanisms without money, assignment mechanisms, and so on. I wanted to just put this up here just to show you that automated mechanism design isn't just for revenue maximization, but the rest of this tutorial is just for the revenue maximization. And maybe this, if you want, this would be a good time to take a 5-minute break for questions. Any questions? We can also just zoom through to the next thing. Yes?
So my question was, could it be related somehow to dynamic pricing? You know, in mobile application settings, mobile games, they somehow figure out the price that will maximize in general, the revenue over some period of time, the revenue of a mobile application.
So that's good. So if the setting is static, turns out that there's no benefit to dynamic mechanisms by the revelation principle. If the setting itself is dynamic, there's actually sometimes benefit to going to dynamic mechanisms. Here in this tutorial, we'll talk mostly about the static case, but in the end, Ellen is also going to talk about some dynamic things, although more dynamic things have been done and could be done. Any more questions? And you can also ask questions for Ellen, by the way, not just for my part.
Maybe there is a chicken-egg situation here when you don't have the incentive compatibility in your original auction, and so you cannot have, in a production setting, you cannot have a sample from that, but you want to design an optimal and also an incentive compatible mechanism. So you need to design the incentive compatible mechanism first to get the samples from the real distribution of the values, and then you can optimize. How do you solve this problem?
Yeah, this is a great question. So we are not saying that the samples that we get from the valuation distributions are bids. We're kind of agnostic where that information comes from. And the way I originally was thinking about automated mechanism design, and how I still largely think about it, is that there's a designer that has some domain knowledge. Like in our sourcing examples, there were people who had been doing the same kind of sourcing for sometimes decades, and they knew the suppliers. So the buyer, the auctioneer in that case, or seller in these auctions, has that information. So it's really the seller that's expressing the prior by samples. The prior here, maybe not from the bids. Now there's a whole other literature in economics. How do you go from bids to values? And there's a lot of work on that. So that's another way you might be able to come up with the samples, but you're exactly right that then you have to worry about how do you actually take into account that the bidders were lying in the original mechanism. But there's a whole economics literature on that. Yes. Go ahead. Oh, yeah.
So in your slide, experiments 2 items, 2 bidders, how sensitive it is to the PDF choice which you have selected? If I understand correctly, you have a uniform distribution here. Did you try other distribution, and is it very sensitive?
Yes, we did try other distributions, and it is very sensitive. And this is kind of the whole point, in that you don't want to be using a general purpose mechanism. You want to be using a mechanism that's specifically tailored to the distributions at hand. Yeah. Oh, I guess.
I had a sort of a two-part question. You mentioned that randomized mechanisms are easier to solve for than the deterministic mechanisms, computationally speaking. Are those randomized mechanisms sort of analogous to mixed strategies in Nash equilibria? And have you looked at all into whether those randomized strategies can actually perform better in terms of, say, revenue maximization than the deterministic strategies?
Yes, so when you're in a table-based representation, the randomized mechanisms are easier because they're linear programs instead of integer programs. Then it's known that even for 2 items, the optimal mechanism has to be randomized, while for 1 item it's not. This was actually something that was open in the literature for a while, and in 2003 we had this little workshop paper where we had actually used automated mechanism design to figure that out. So you can actually say, okay, take a setting, run a randomized, optimize a randomized mechanism into it, optimize a deterministic mechanism into it, and voila, if the randomized one gives you more revenue, you've just proven your conjecture. And you can do this by randomly generating settings, and if it happens even in one setting, you've proven your theorem. Now, yes, so you were asking about revenue. Yes, even in 2 item settings, you can get higher revenue with randomized mechanisms. Now, we don't really have a good space of randomized mechanisms to optimize over, like we have the affine maximizers here or VVCAs, but the theory that we'll talk about later in this tutorial applies to randomized mechanisms as well. Should we take one more question? Let's take one more question in the red shirt there.
Thank you for the talk. I heard Helen mention that carefully chosen reserve prices can actually substitute for complicated auction logic in 1 item auction. So does it hold in multi-item auction that you can basically learn reserve prices for each participant, for each bundle, for example?
Oh, okay, good question. So now, to keep this lively, I'm going to say that your assumption is false. So this is a common misunderstanding that in 1 item auctions, you can actually get optimal mechanism with reserve prices. That is true only if you have a symmetric distribution. Then the optimal mechanism is a Vickrey auction with an optimally set reserve price. But when you have different priors, it's not the case. So even in the single item setting, you benefit from doing other things than reserve pricing. And here, reserve pricing doesn't have the full power. And we showed, for example, that even if you combine reserve prices with mixed bundling auctions, And then even if you go from there to the more general class of VCAs, that doesn't give you the full power. You have to go beyond that. AMAs have even more revenue than that. Thank you.
All right, so can you guys hear me? Can you hear me, please? I'm not as tall as Tuomas. Just want it a bit farther away, not close to me. I want it a bit farther away. Okay, great. All right, so in the next part of the tutorial, we'll be talking about sample complexity guarantees for automated mechanism design. So Tuomas nicely described what automated mechanism design is, and he talked about computational complexity consideration or optimization consideration. Now, next important question is a sample complexity question, and this is what I'll talk about next. And I'll specifically be focusing on the distributional learning scenario, and then Ellen will tell us about some other settings as well. Okay? And so, just to remind you, we can view mechanism design as a learning problem as follows. So, what we do, we fix a problem that we want to solve, say the problem of pricing one or multiple items for sales in order to maximize revenue, which is really the focus of this part of the talk, of the tutorial. And so we fix a problem that we want to solve, and then what we do, we fix a parametric family of mechanisms that is commonly used in practice for this problem, or that we hope will do well for this problem. And then what we do, we take a sample, as Tuomas described, from the unknown distribution over the bidder values for various subsets of the items. And then we use these samples in order to find the mechanism that we hope will have high expected revenue with respect to the fixed unknown distribution. Okay? So let me describe this again more slowly. So what we do, we fix a problem that we want to solve, and this can be a pricing problem or an auction problem. And then we fix a large, potentially infinite parameterized family of mechanisms for this problem. So for example, if we are trying to, if we have a single item auction scenario, and we are trying to maximize revenue, we might fix the set of second price auctions with reserve prices, which is what Ellen described at the beginning of the tutorial. Or if we are trying to price multiple items, again, to maximize revenue, we might consider the set of all posted pricing mechanisms, which again, Ellen described at the beginning of the tutorial. Oops. Okay, and so we fix a problem that we want to solve. We fix a large, infinite parameterized family of mechanisms for these problems. And actually, the family of mechanisms that I gave as examples here are actually infinite. For example, because for the reserve price case, second auction price of reserve prices, the parameter itself is just can take continuous values. Okay, and so and then what we do, we take a set of samples which we assume that are drawn at random from this fixed unknown distribution over the buyer's values for various subsets of the items. So, for example, in the second price auction with reserve prices case, our samples, because we are selling just one item, our samples will just describe the value of each buyer for the given item. Okay, so this will be sample number one, where we get the value of each buyer for each of the items, and so on. We have sample number n. So you have, say, capital N samples here, or this is for the second price auctions of reserve prices, or if we are doing posted price mechanisms where we are selling multiple items, where we have multiple items for sale, our samples will look a little bit more complicated. So each sample will tell us for each subset of the values of our buyers for each of the subsets of the items. Okay? So this is sample number 1. So if we have 2 items, sample number 1 will tell us for buyer 1 how much he values, say, the coffee, how much he values the muffin, and how much he values both the coffee and the muffin. And similarly for buyer number 2, and so on, buyer number n. And so this is one sample, and we'll get capital N such samples. Okay, and then our goal is to use such samples, again, in order to find the mechanism, but we want this mechanism to have high expected revenue over the underlying distribution. So more precisely, we want to find the mechanism whose revenue is as close as possible as the revenue of the best mechanism from this family of mechanisms with respect to the underlying distribution. And again, we want to do this by only using samples. Okay? So that's the goal. And as Tuomas described, a natural approach in order to solve this problem is to try to find the mechanism, let me call it M hat, that is nearly optimal over the set of samples that we have seen. Okay? So that's a very natural approach. But of course, a key question is if this mechanism that does very well over the training set of samples that we have seen will actually have high expected revenue with respect to the underlying distribution. And will this mechanism be close to the best mechanism with respect to that hidden unknown distribution from this family of mechanisms? Okay, so that's a key question. And right, so for example, for the case of second price auctions of reserve prices, well, we know that the reserve price that we picked has good, the mechanism that we picked does well over the training set of examples, has high revenue on average over the training set of examples because we've chosen it to do so. But of course, the key question is, will it have high revenue on a new random sample from the same underlying distribution? Will it have high expected revenue on a new random sample? Okay, so that's a key question, and of course the answer to this question will depend on how many training samples we've seen in the training set. And so that's basically exactly a sample complexity question, which is how many training samples we need to see in order to guarantee that that a mechanism that does well over the training set of samples will also have high expected revenue as well. Okay, and this is exactly where learning theory, so these are the types of questions we always study in machine learning, in learning theory in particular, and so it's very natural to try to use techniques from learning theory in order to address this question. And indeed, there is a recent line of work in various communities that does exactly this. And in particular, a lot of the work in this area has been focused on so-called uniform convergence bounds, which are sample complexity bounds that quantify how many training examples we need to see so that uniformly for all mechanisms in our class of mechanisms, we have that with high probability their average revenue over the samples is close, say additively epsilon close to their true expected revenue with respect to the unknown distribution. Okay, this is what uniform convergence bounds are, and they are very nice because once we have uniform convergence, once we've seen enough samples to get uniform convergence, then we are guaranteed that if we optimize over the training set of examples that we are given, we're going to get high expected revenue as well. Okay, and okay, and so that's pretty much like a learning, to some extent, a learning theory question here. How many training samples do we need to see in order to get uniform convergence? And we know from learning theory, and again, I'm going to just give this the high level and simple here, but we know from learning theory that the number of samples we need to see in order to get uniform convergence depends somehow on how intrinsically complex the class of mechanisms that we are looking at is. Okay, and there are many notions of complexity that we have in learning theory. For example, the VC dimension for binary valued functions, the pseudo dimension for real valued functions, the Rademacher complexity, and so on. And the key point is that this notion of dimension then comes in the uniform convergence bounds. And what is, and I want to point out that a lot of the recent work in this area is actually trying to compute the notion of dimension for the various mechanisms classes that come in the context of automated mechanism design. And what I want to point out is that actually there are some specific challenges to these scenarios. In particular, the revenue functions here have structure that is unusual in machine learning. In particular, they have discontinuities, they're asymmetric, they are given by complex combinatorial modular mechanisms sometimes, like AMA that Tuomas described. So we really need new techniques to understand the intrinsic dimension of this family of mechanisms. Okay, and there is a recent line of work that is doing exactly this. So I have several references here on my slide on this topic. Actually, the very first paper that looked at analyzing the complexity of mechanisms in the context, in kind of this automated mechanism design scenario, is an older paper that I have joined with Avrim Blum, Jason Harline, and Ishai Mansour. And here we're looking at the specific settings where we had unrestricted supply of our goods. So these are called digital goods. Okay, so this was more than 10 years ago, but more recently, there has been a surge of work, an explosion of work on trying to understand the intrinsic complexity of mechanisms for more delicate scenarios, or you have multiple items for sale and combinatorial preferences and limited supply. So for example, the paper by Mehri Armori and Andres Medina in IPS 14 looks at analyzing the pseudo dimension and also the market complexity of second price auctions and reserve prices, or work by Tim Ravgarden and Jamie Morgenstern looks at analyzing the pseudo dimension of several simple auctions that are generalizations of or inspired by the Meyers auction. Recent work by Tuomas, Ellen and I that appeared in EC this year gives actually a very general theorem for finding the pseudo dimension of many, many mechanism classes. And there is also other work that analyzes other notions of complexity, like Rademacher complexity or some sort of covering numbers, again, for these mechanism classes. Okay, so there is a lot of interesting recent work on the topic. What we're going to do next, we're going to give you a high-level, gentle description of some of the results in this EC18 paper. Okay, but before doing so, just to make sure that we're on the same page, I'm going to do a quick 5 minutes reminder of what VC dimension and pseudo dimension are using pictures. Okay, so when we are trying to understand the complexity of binary valued functions like linear separators in RD, right, that are just functions that label things, say, on one side as positive and on the other side as negative, right? So when we are trying to understand the complexity of such classes of functions, we typically use the VC dimension, which is a measure that exactly characterizes the sample complexity of binary valued function classes. Okay, and what is the VC dimension? Well, the VC dimension of a class H is just the cardinality of the largest set S that can be labeled in all possible ways by functions in H. Okay, and if a set can be labeled in all possible ways by functions in H, we say that the set is shattered, right? So it can be shattered or can be labeled in all possible ways by functions in H. And again, the VC dimension is just the cardinality of the largest set S that can be labeled in all possible ways by functions in H. So for example, the VC dimension of linear separators in R2 is 3. Turns out that you can show that any set of 3 points that can be put in a triangle like this can be labeled in all possible 2 to the 3, which is 8 ways by linear separators. So for example, if I want to label this guy here, oops, here's my part. Yeah, if I want to label this guy as, say, plus, and this other 2 as minus, I can just use this linear separator here, and you can show that all the labelings are achievable. So we can, there exists a set that can be labeled in all possible ways by linear separators. There exists a set of 3 points that can be labeled in all possible ways by linear separators in R2. But we can also show that no set of 4 points can be labeled in all possible ways by linear separators in R2. So in particular, there are just 2 cases. If one of the points lies inside the convex hull of the others, then we cannot achieve the labeling where this guy is negative and all these other 3 points are positive. or if none of the points lies in the convex hull of the others, then we cannot achieve this labeling, or these 2 points are labeled, these 2 opposite points are labeled as positive, and the other two opposite points are labeled as negative. Okay, so basically we can show that no set of 4 points can be labeled in all possible ways by linear separators in R2, but there exists a set of 3 points that can be labeled in all possible ways by linear separators in R2, so the VC dimension of linear separators in R2 is 3. And more generally, you can show that the VC dimension of linear separators in RD is D plus 1. Okay, these are just examples to remind you what VC dimension is. Now, for our case, our functions are not binary valued functions, they're actually real valued functions, so we need a measure of complexity that is tailored to real valued functions. And the measure of complexity that we're going to talk about in this tutorial is the pseudo-dimension, the so-called pseudo-dimension of a class of functions, which is really just the natural analog of VC dimension, is the natural extension of VC dimension to the case of real valued functions. Okay, and what is the pseudo-dimension of a class of functions F? Well, it's just the cardinality of the largest set of points that can be shattered in a real value sense with functions from our class. Okay, so more specifically, the pseudo-dimension of a class of functions F is just the cardinality of the largest set S of points, x1, x2, xn, along with thresholds y1, y2, yn, such that all 2 to the n above and below patterns can be achieved by functions in F. So just to give an example, so for example, if n equals 2, what do I mean by above and below pattern here? If n equals 2, we would need, in order to be able to say that we shatter 2 points by these functions in our class, we need to show that there exist points x1, x2, and threshold values y1 and y2, such that all 4 above and below patterns can be achieved. By this I mean there exists a function f1 that achieves a below pattern, which means that f1 on the point x1 is strictly smaller than y1, and f1 on x2 is strictly smaller than y2. There is also a function f2 that achieves the above and below pattern, which means that f2 of x1 is greater than y1, and f2 of x2 is smaller than y2. There exists a function f3 that achieves the below and above pattern, and finally there exists a function f4 that achieves the above pattern. Okay, so this just means, so again, the pseudo-dimension of a class of real valued functions F is just the cardinality of the largest set that can be shattered in a real value sense by functions in F. And if you think about it, actually, equivalently, the pseudo-dimension of a class of functions F is just the VC dimension of the below the graph function, where what we do, we just add y as an additional feature to the example x, and then the value of the function is just the sign of f of x minus y. So any point below the graph of the function will be labeled as positive, and any point above the graph of the function will be labeled as negative. So it's just very natural. But the notion that we're going to use, like the intuition that we'll use throughout the tutorial, is this notion of shattering in the real value sense. So let me just give you one more example. So for example, one more pictorial example. So for example, the class of affine functions on the real line, which are functions of this form, just simple affine function on the real lines. So this class of affine function can actually shatter in a real valued sense 2 points. In particular, it can shatter these 2 points over here, x1 and x2. Why? Because there are these thresholds y1 and y2, and there exist these 4 functions, f1, f2, f3, f4, that achieve all the above and below patterns. Right? So for example, the function here, f1, achieves the below pattern, which is because f1 of x1 is strictly smaller than y1, and f1 of x2 is strictly smaller than y2, right? And then there are also these other 3 functions, f2 that achieves the above-below pattern, f3 that achieves the below-above pattern, and f4 that achieves the above-above pattern. Right? So this is another pictorial example of 2 points that can be shattered in a real value sense by affine functions over the real line. And you can show that no 3 points actually can be shattered, so the pseudo-dimension of affine functions will be, in this case, 2. Okay? So this was just a quick reminder of learning theory, like this dimension and pseudo-dimension, but let's see it in, actually before seeing it in action for auctions, let me just tell you how this pseudo-dimension is used to then get uniform convergence bounds, which are the type of bounds we are after. So what are uniform convergence bounds? Are simply bounds that of this form. So they are bounds that tell us how much the expected empirical value of a function differs from its true expectation for any given, and we want these bounds to hold uniformly for all the functions in our class of functions. And what this uniform convergence bounds based on the pseudo-dimension tell us is that for any fixed unknown distribution over the instance space, so if we first fix a class of functions f, then for any fixed unknown distribution over the instance space, then we have it with high probability. If we then draw a random sample x1, x2, xn, capital N here is the number of samples, then with high probability at least 1 minus delta over the draw of this training sample, we have it uniformly for all functions in the class where empirical average deviates from the true average by no more than this term here, which is roughly square root of the pseudo-dimension of the class of functions over the number of samples. Okay, so this deviation can be upper bounded by the square root of the pseudo-dimension of the class of functions over the number of samples. Okay, so the simpler so one way to think about it is that the simpler the class of function is, the less samples we need to get this deviation to be small. Okay, and so this is a classic result, uniform convergence result based on the pseudo-dimension. Okay, and this is a classic result from learning theory. And so now going back to our mechanism design context, I want to show you how we can actually compute the pseudo-dimension of certain classes of functions, of mechanism classes that come from automated mechanism design. Okay, and what I'm going to do, I'm going to show you an example. I'm going to show a high-level sketch of a proof for a simple example for the case of second price auctions with reserve prices. And then I'm going to state a very general theorem that applies to all sorts of mechanisms. Okay, so going back to mechanisms, so let's assume that we are doing, we just have one item for sale, and we have multiple bidder scenario, and we are thinking about the class of auctions that are second price auctions with reserve prices. So as Ellen, so just to remind you, as Ellen mentioned, in this case, here's what we do. So the auctioneer sets a reserve price R, and if the highest bidder, and then the highest bidder wins if his bid is greater than R, and the payment that he makes is a maximum of the second highest bid and the reserve price R. Okay, and we can show that actually the pseudo-dimension of this class of functions is not too large. It's actually only a constant. Okay, and actually the key insight for, or one of the key claims for showing that is the following. So what we can show is that, so that's a lemma, a useful lemma, we can show that if we fix a set of bids, so if we fix just a set of bids, so how much is each buyer willing to pay for the item, and then if we imagine varying the reserve price, we can draw like a revenue curve, right? So if we fix a set of bids, and then if we just imagine varying again the reserve price, we get a curve, a revenue curve. Well, the claim is that this revenue curve is piecewise linear with 3 pieces. Okay, and here is quickly why. Well, because let's fix our set of bids, and let's assume that the second highest bid lies here, and let's assume that the highest bid lies here. Well, when the reserve price is smaller than the second highest, so when the reserve price is greater than the second highest bid, then we know that the highest bid wins, the highest bidder wins, and he pays the second highest bid. So that's why we get this part over here, this part of the curve here. Well, when the reserve price is in between the second highest bid and the highest bid still wins, the highest bidder still wins, but he pays the reserve price. That's why the revenue function looks like this identity function in this part of the space. And finally, when the reserve price is greater than the highest bid, then nobody wins and nobody pays anything, so our revenue is 0. Okay? So what we've just shown is that for second price auctions with a reserve, if we fix a set of bids and then we plot the revenue function when we vary the reserve price, it has this very nice, simple structure, which is a piecewise linear function with 3 pieces. Okay? Now using this, we'll be ready to give you a quick sketch of why the pseudo-dimension, the intrinsic dimension of this class of auctions is not too large. And by the way, this is probably the most technical part of the tutorial, but I'll try to explain it at a high level still. Okay, and so actually the proof is not, the outline is kind of simple. So what we're going to do, so I want to show that the pseudo-dimension of the class of reserve prices, the pseudo-dimension of the class of second price auctions of a reserve is at most 2. Okay, so let's try to reason about that. So let's first fix a valuation vector and the threshold revenue yi, right? Because we are trying to think about somehow shattering this point. Okay, so what we know from the previous slide is, well, is that if I fix the valuation vector, vi, then, well, the revenue, and if I then value the reserve price R, then the revenue function is this piecewise linear function with these 3 pieces of looks. This basically blue curve in my picture here. Okay? Now, let's imagine scanning the reserve price from 0 to infinity. Now, we notice that there are at most 2 critical points, 2 cutoff values, C1i and C2i, where the revenue goes from below yi to above yi, and then again back to below yi. Okay? And so this is for one valuation vector. Now, if we have, for one example, for one sample, now if we have n samples, we'll have 2 times n cutoff values, 1 for each sample. And the key insight is that for all reserve prices are in the same interval between 2 consecutive cutoff values, so all such reserve prices in the same interval between 2 consecutive cutoff values will give the same above and below above or below pattern with respect to our n samples. So what this says is that if I give you n samples, we can achieve at most 2 times n plus 1 binary patterns, above and below patterns. Okay, but now recall that the pseudo dimension of a class of functions is just the cardinality of the largest set for which all 2 to the n binary patterns are achievable. And so if I want to compute the pseudo dimension, that means I need to find the largest value of n for which 2 to the n is upper bounded by 2 times n plus 1. Because I just argue that given n samples, at most 2 to the n plus 1 binary patterns are achievable. Okay, and when I solve this little inequality here, I can just show that n is at most 2. Okay, so that was pretty much a quick proof of why the pseudo dimension of the second class of second price auctions and reserve prices is only a constant. Okay, and this proof, by the way, has been shown by several people, or not necessarily this proof, but this result has been shown by several people, including Mehri Al-Mouri and his former student Andres Medina, Tim Ravgarten and Jamie Morgenstern. Is also implicit in our own work. The proof that I showed you here, it's the cleanest proof that I know, and it's actually the proof that motivated a very general theorem that applies to many, many mechanisms that can be very easily stated pictorially. So now what we do, we go to very general mechanisms that are parameterized by vectors that are potentially in RD. So the previous case, we had just one parameter, real value parameter. Now in general, we can have many real value parameters. If we do positive price mechanism, or if we do often maximizer auctions and so on, we'll have many more real value parameters. Okay, so let's think about such a class of mechanisms parameterized by vectors P that live in RD. And let's assume that we have the following structure property, that for every set, if we fix a set of Bayer's values, so if we fix a sample in a machine learning term, so if we fix a sample, then there exists a set of at most T hyperplanes that partition the parameter space in such a way that inside each of the parts, the revenue function is linear. So in other words, what we say is the revenue function is the piecewise linear functions where the pieces are just given by intersections of hyperplanes, really. Okay? If that's the case, then we can show that the pseudo dimension of this family of mechanisms is actually kind of small. It's only order of d log dt. So d here is the dimension of the parameter space. And notice that so this appears in the pseudo dimension bounds, but the dependence on number of hyperplane is actually very small. It's only logarithmic. Right? So that's an interesting result we can show. And just to connect this to the previous example that I had with second price auctions. So here, T, so we had a piecewise linear functions with 3 pieces. So then that theorem, of course, would apply to second price auctions as well. Second price auctions are reserve prices as well. But in general, you might have, again, maybe rather than just having D to be 1, as we had for second price auctions and reserve prices, we might have D2, like I have in this picture here. For example, if I'm doing posted prices for 2 items, and maybe the number of hyperplanes might be 5, for example, like in this picture here, okay? This is just a toy example, by the way. Ellen will show you many interesting examples that come from mechanism design in a couple of minutes. Okay, but actually before having Ellen present other cool applications of this general result, I just want to mention that I'm not going to go through the argument or anything like that, but I just want to mention that at a high level, so for some learning theorists in the audience, because I see there are some learning theorists in the audience, I just want to mention that at the high level, what's kind of actually interesting, so the proof what's interesting about the proof is that we have a structural result, we assume a structural result really about the dual class of functions, and then we get a pseudo-dimensional result about the original class of functions. Okay, I'm just going to state this and don't go into details, but it has a very cool high-level learning theory aspect here too. Okay, but because this is a tutorial about mechanism design, I'm going to stop here about talking about the learning theory aspects, and I'm going to have Ellen present many other cool applications of the theorem.
So Nina talked mostly about second price auctions with reserves, and now I'm going to go and tell you about some applications of this main theorem to multi-item settings. Multi-item and multi-unit. Okay. So the first one I'm going to talk about is posted price mechanisms, which we saw before. So, and just to remind you, what this general theorem is basically saying, in a summary, is that if our parameter space is d-dimensional, so if our mechanisms are defined by some d parameters, and if there are t hyperplanes splitting this parameter space into regions where profit is linear, or revenue is linear, then our pseudo-dimension is basically d log dt. Okay, so let's remember what posted price mechanisms are. So these are multi-item and multi-bidder, multi-buyer. We're going to set a price per item, and we're going to assume there's some fixed but arbitrary ordering over the buyers. And the first buyer is going to arrive, buy the bundle of goods that maximizes his utility, and again, utility is their value for the bundles minus the price. Then the second buyer is going to arrive, buy the bundle of remaining goods that maximizes their utility, and so on. And posted price mechanisms have been studied extensively in the Econ CS community. And so what we prove is that the dimension of this parameter space equals the number of items. And I'm sure you can see that. That's just because we get to set number of items prices. We get to set one price per item. So the dimension of our parameter space defining this mechanism class is the number of items. And then the number of hyperplanes splitting this parameter space into regions where profit is linear on any fixed set of buyer values is the number of bidders times 2 to the 2 times the number of items. And that's basically because for every bidder, you can look at, for every pair of bundles, in which part of the space would they prefer to buy one bundle over the other. And so we've got basically 2 to the number of items, choose 2 comparisons to make. And we can formalize these comparisons as hyperplanes. But then we can just stick this d and t into our general theorem, and that gives us a bound on the pseudo-dimension, which is basically number of items squared. And this matches a bound by Morgenstern and Roughgarden. And so another class of mechanisms we look at are randomized mechanisms. So these are often called lotteries. And these are multi-item and single buyer, but they can be generalized to multiple buyers. And we're going to assume the buyer is additive. They're generally defined for additive buyers, which means that a buyer's value for a bundle is the sum of their values for every item in that bundle. And so a lottery is represented by a vector, phi1 up through phi number of items, so it's a number of items dimensional vector, and a price p. And the way it works is that if the buyer chooses to buy the lottery, they're going to pay a price of p, and they're going to receive each item I with probability phi I. So a way that the seller can get even more revenue is by offering a menu of lotteries. So this is where the seller is going to offer the buyer multiple lotteries, and the buyer is going to choose whichever lottery maximizes his expected utility. And his expected utility is just sum over all items, his value for the item, times the probability that he gets that item, minus the price. So he's just going to choose to buy whichever lottery maximizes his expected utility. So lotteries have also been studied very extensively in Econ CS. And what we prove, and I won't really go through this, it kind of follows the same intuition as the previous slide, but what we prove is that the dimension of this space is number of items plus 1 times the length of the lottery. So if you're offering a length, if you're ordering capital L lotteries to the buyer, that's the dimension of this space, and the number of hyperplanes is number of lotteries squared. And so a corollary of our general theorem is that the pseudo-dimension of this class of length L lotteries is basically the number of lotteries times the number of items. Another example of a mechanism class that we can apply this general theorem to is two-part tariffs. So here, these are single item, multi-bidder, and there are multiple units of each item for sale. So that what the seller is going to do is set an upfront fee, PO, and a fee per unit, P1. And if the buyer buys K units of the good, they're going to pay the upfront fee plus K times the price per unit. And you see these all around in the real world. So for example, when you sign up for the gym, you're often going to have to pay some kind of upfront membership fee and then a fee per month. So these are all over the place. So the buyer is going to buy the number of units that maximizes their utility. And again, just like with lotteries, the seller can possibly get more revenue if they offer a menu of lotteries. So, or a menu of tariffs. So he's going to offer many different tariffs that the buyer can choose from, and the buyer is going to choose the tariff and the number of units that maximizes his utility. So a different tariff corresponds to different choices of the upfront fee and the fee per unit. These have been studied for decades in economics. And so again, if you're offering a menu of L tariffs, the dimension of the space is 2 times L, and the number of hyperplanes, splitting the parameter space into regions where profit is linear, equals the number of buyers times L times the number of units squared. And just as a corollary of our main theorem, we get that the pseudo-dimension of this class of length L lotteries is basically the number of lotteries. And here, just to be clear, the number of units is the total number of units for sale. Okay. So going back to affine maximizer auctions, which Tuomas talked about in his part of the tutorial, we can also apply our general theorem to give pseudo-dimension bounds for affine maximizer auctions. And as you might remember, affine maximizer auctions are pretty complex, and so it shouldn't be a surprise that our pseudo-dimension bounds are pretty large. So here's our bound for affine maximizer auctions. Here's our bound for virtual valuation combinatorial auctions. And there are also subclasses where we get better pseudo-dimension bounds, subclasses that have been studied previously in economics. So for example, mixed bundling auctions are basically a subset of affine maximizer auctions. Remember, affine maximizer auctions are a class of generalized VCG auctions where you get to boost the social welfare of a set of allocations, and you also get to multiplicatively boost every bidder's bids. And mixed bundling auctions, you are only allowed to boost those allocations where some buyer gets the grand bundle, gets all of the items. So you'll have a very kind of constrained optimization space. And then there are also classes that sit kind of in between this very simple class of mixed bundling auctions and the more general classes. And these also have relatively nice pseudo-dimension bounds. And last, there are also many other auction classes that this general theorem applies to, but which I'm not going to talk about right now. So these include multi-item, multi-unit, nonlinear pricing mechanisms. So these like generalize the two-part tariffs. And they also include lambda auctions, which are a subset of affine maximizer auctions. Okay, so as we saw, affine maximizer auctions are very complex, but they contain kind of nice hierarchies, breaking them up into simpler subclasses. And it would be really nice if we could somehow take advantage of the simplicity of these hierarchies to get even better guarantees in some cases. So this is what structural revenue maximization allows us to do. Okay, so for example, remember affine maximizer auctions, we get to boost additively the social welfare of a bunch of allocations. So you could imagine, what if I looked at the subclass where only one allocation is boosted, or 2 allocations, or 3 allocations? So this is going to create a nested hierarchy of affine maximizer auctions. And since it's a nested hierarchy, the complexity of each growing class is going to get bigger and bigger and bigger. And we can quantify this complexity using pseudo-dimension, which I've plotted as a hypothetical example on the x-axis here. And what I'm plotting on the y-axis here is various revenue curves. So the top solid line, I've found the empirically optimal mechanism in each of these subclasses and plotted its empirical revenue. And since this is a nested hierarchy, the empirical revenue is just going to get better and better and better as I go outward. But as we learn in our very first machine learning course, at some point, as my mechanism class gets more and more and more complex, I'm going to start overfitting. So this is what's happening when the expected revenue curve, which is this dotted curve, starts to diverge from the empirical revenue curve. I've started overfitting. So what structural revenue maximization at a very high level allows us to do is see when we've started overfitting. So what structural revenue maximization allows us to do is formulate a lower bound on expected revenue, which is complexity dependent. So it's the empirical revenue minus some complexity dependent term, which is based on the pseudo-dimension of that individual subclass. So structural revenue maximization is basically the process of optimizing this trade-off between revenue maximization and also keeping the class simple. Okay, so, and this might sound familiar, this kind of like model selection framework. And of course, structural revenue maximization builds off of a whole rich literature on structural risk minimization in more general in machine learning. So I'm just going to give you an example of what structural revenue maximization can look like. So again, let's think about the class of affine maximizer auctions, but let's break it into a hierarchy of simpler classes, which I'll call k-sparse affine maximizer auctions. So k-sparse affine maximizer auction is where I only boost k allocations at a time. Okay, so what our general theorem that Nina presented allows us to show is that if m hat k is the empirically optimal k-sparse AMA, so it maximizes average revenue over the samples, and mk star is the optimal k-sparse affine maximizer auction, so it maximizes expected revenue, then the expected revenue of this empirically optimal affine maximizer auction is at least the expected revenue of the optimal one minus this complexity-dependent term. And so this complexity-dependent term depends on the number of bidders, the number of items, K, which is the sparsity, and the number of samples. And U is an upper bound on revenue over the support of the buyer's valuation distribution. So this complexity-dependent term is going to get worse and worse and worse the further out in this hierarchy you get, but the revenue of the best k-sparse AMA is going to get better and better and better. So you're basically optimizing this trade-off between revenue and keeping the class simple and overfitting, basically. So this is kind of the power of structural revenue maximization. Okay, so that's all we have for this kind of theoretical guarantees for automated mechanism design. And now I want to talk about a few kind of special purpose algorithms for automated mechanism design, specifically for the single item case and also for ad auctions. And actually, unfortunately, just due to time, I think I'm going to have to skip over the empirical Meyers section, which is for the single item case, but it's a beautiful line of work, and you can find, we'll post the slides very soon so you can find them online. And I'm going to go quickly through ad auctions. So as we saw, ad auctions generate huge amounts of revenue for big internet companies. And the way it works at a very high level is that when you visit a site, so the site is going to send a request to an ad exchange for an ad. And an ad exchange is basically just a marketplace for ads. That ad exchange is going to begin a real-time auction, and the ad networks, the advertisers, are going to bid on the impression for sale. And the impression is the opportunity to show you an ad. Then the winning advertisement is going to be displayed to you. And this whole process just takes milliseconds to complete. There's been a ton of work on ad auctions, especially beginning in 2006, 2007. And I'm just going to talk about one that relates really nicely to this automated mechanism design literature and which has kind of an intuitive explanation behind it. So the key challenge in designing ad auctions using data is that there's literally trillions of different items for sale. Each item is an impression, an opportunity to show you an ad. And so it's likely that a specific item has never been sold before, so you might not actually have data points on that specific item. And just to be slightly more concrete, people often represent an impression, that opportunity to show you an ad, using a feature vector, and that feature vector is going to include features such as the ad size, whether that ad is on a mobile or a desktop. And the underlying assumption is generally that bids for two similar feature vectors are going to be similar. So this line of work kind of formalizes this intuition. So I'm particularly going to talk about nice work by Medina and Vasilevitsky from NIPS 2017. And in their model, there's a single buyer and a single item, which is this, or a distribution over items, which are these feature vectors. So in particular, there's a distribution over feature vector value pairs. So the feature vector Z describes this impression, and V is the value. And there's a joint distribution over this domain. Okay, and how this auction is going to work is that the auctioneer and the buyer are both going to observe this feature vector describing the impression. The auctioneer is going to choose a price for this impression. Maybe it's a quarter. The buyer is going to have some value for that impression. Maybe it's a half. And the buyer is going to buy the impression and pay the price if and only if their value is greater than the price. So if their value is 1/2, the price is a quarter, they're going to buy it. But if the price goes up to 3/4, they're not going to buy it anymore. So the question is, how do we learn a good price function P that maximizes revenue? Expected revenue over this distribution. So the assumption that Medina and Vasilevitsky make is a pretty nice one. It's pretty reasonable. Their assumption is that there exists some bid prediction function. You have access to this function a priori that predicts, given a feature vector Z, what is the bid going to be. And the assumption is that this bid prediction function has good L2 error, basically, an expectation over this distribution. In particular, it equals some eta squared for some eta. And you could presumably use some selection of historical data and some standard learning algorithm to learn such a bid prediction function. Okay, and then given this bid prediction function, their pricing algorithm looks like this. Remember, we want to learn a good pricing algorithm that takes as input a feature vector and returns a price. So the input to this algorithm is a set of samples from this distribution and a parameter k. They cluster. You take your bid prediction function and you evaluate each feature vector. And you cluster these evaluations into k clusters. And these are all points on the real line. So this clustering is basically going to correspond to a partition of 0, 1 into k intervals. So you can see this here. And now we have these clusters, we have these intervals. We're going to assign a price per interval. And the way we're going to do that is take the empirically optimal reserve over all the vi such that h of zi falls inside of that interval. So that's the price we assign to the interval. And then on a fresh feature vector z, we're going to charge the reserve price of whatever interval h of z falls into. So that's their pricing algorithm. That's how they come up with prices based on the sample. And that's just an informal representation of their algorithm. And they give some guarantees, which just for the sake of time, I'm going to skip. But basically, they relate the revenue loss due to their learning procedure to the, how good their bid prediction function is. And they give some experiments on ad exchange data. And so they have 3 algorithms here. DC, which was proposed by Mori and Medina in ICML2018, offset, which is a simple algorithm they proposed as kind of a warm-up in this paper from NIP 17, and their own algorithm, RICH. And you can see that they've normalized it. They've normalized this, the revenue so that DC is 1, and in general, RICH is going to obtain a 30% revenue lift over this DC algorithm. So that's all I want to say for now about ad auctions, and we're just going to wrap up for now with just describing at a really high level a few more learning frameworks, which unfortunately we don't have time to talk about in depth, but they could be tutorials in their own. So the first of which is online learning, where basically you as a seller get to set a price every day, and you see what did the buyers buy, what revenue did you get, and you use that to update the next price you're going to set on the next day. And you want to minimize regret, which is the standard notion of regret. You want to minimize the difference between your cumulative revenue over the course of all of these time steps and the cumulative revenue of the best price in hindsight. So that's just a standard notion of regret from all of online learning. And this can also not only be related to prices, but also maybe auctions and so on. And there are a lot of different kind of viewpoints you could take on online learning for auction design. For example, maybe the buyer's values are adversarial, maybe they're stochastic, maybe the buyers are being truthful at every single time step, or maybe they're being strategic in that they know they're a part of some repeated auction and they're being strategic to get better prices in the future. And this is just a tiny subset of the works that have been looked at in this arena. And in a related setting are profit inequalities and secretary problems. So in online learning, you sell the same items every single day. New items you just sell the same items every single day, repeatedly. But in the profit inequality and secretary problems, you have a fixed set of items that you're trying to sell. And in the profit setting, the buyers arrive in an adversarial order, but their values are stochastic. Whereas in the secretary problem, the buyers arrive in a random order, and they have adversarial valuations. So these are two kind of different takes you can take on this kind of problem of selling fixed items in a kind of repeated auction setting, or in a setting where buyers are arriving online. And another setting, which is similar to online learning, but kind of from a flipped perspective, is learning to bid. So the online setting I described in the previous slide is where you're the seller interacting with buyers repeatedly. But here, what if you take the viewpoint of the bidder, who maybe doesn't know their value for the items? So for example, in online advertising, maybe you don't know if a buyer is going to click on your ad, so you don't actually know what is your value for the opportunity to show that buyer an ad. So in learning to bid, you basically want to minimize regret, regret being the difference between your utility had you found the best bids to bid over the course of the entire auction, minus the utility you got when you used the bids you actually did use. And the last learning framework I want to talk about is learning from revealed preferences, where you have some set of divisible goods like gold and diamonds. You set some price per unit, and you see what the buyers bought. And you do this again and again and again. And then on the last day, you say, well, what if I had set the price of gold to be $6, the price of diamonds to be $4? What would the buyers have bought? So you can basically view your interactions, your previous interactions with the buyers, as a training set, which you use to basically learn their valuation function so you can answer for what price, on these prices, what would they have bought? And there's been a long line of work on this, also exploring very interesting questions like how many training samples should I use? How do I actually learn the buyer's values? Okay, and just in the last 2 minutes, I want to give a few future directions for this line of automated mechanism design. So one kind of natural next step is giving more optimization algorithms for automated mechanism design. And there are lots of questions here, and in particular, one sub-problem would be specific to structural revenue maximization. So the slide on structural revenue maximization I gave a high-level overview of gives you guarantees for structural revenue maximization, but it doesn't actually tell you how to optimize over the hierarchy in a smart way. So how can you actually do this kind of optimization procedure? This has been kind of the challenge of structural risk minimization in machine learning for decades. Another really interesting question would be to give beyond worst case guarantees for these learning theory problems. So sample complexity bounds that are even better when the buyer's values are drawn from kind of a well-behaved distribution. And so, for example, this might be using tools like Rademacher complexity, which has been explored a little bit so far, or maybe covering style analyses. So people have started to think about this, but there's still a lot of really interesting and well-motivated questions here. And then, of course, automated mechanism design for objectives beyond revenue maximization, and also studying automated mechanism design for problems that aren't even related to selling. So with that, thank you, and we'll take any more questions if you have any.